combining my like terms, 8 plus 1 is going to be 9. We want to make certain to keep the grouping symbol there because we still have our negative out front. As I distribute that negative through, we end up with negative x squared minus 4x minus 4 plus 4x plus 9. And where maybe this starts to become enjoyable or fun, we can absolutely combine like terms. The negative and positive 4x are going to cancel. Our negative 4 plus 9 leaves us with negative x squared plus 5. So g of x plus 2 is equal to negative x squared plus 5. All right, so again, that's our our evaluation of functions within that function notation. The last thing we need to talk about here, like I said, we're going to hit on this a little bit more tomorrow, but a piecewise function. It's going to be a function defined by, we got cut off there, by 2 or more equations over a specified domain. Now, I realize that gets a little wordy pretty quickly, but what that means is that as we look at this example, that we are not just, I don't know, I'm tempted to go ahead and draw the sketch here. In fact, I think now as I have a little bit of time, I may do that. So if I were to sketch this out, hopefully, again, you are all very okay with the roughest of rough sketches. But as I'm looking at this, if I would have been having this thought ahead of time, I would have just pulled a graph. That probably, if I'm being honest, would have made more sense. But we're going to make the most of it here. So we'll worry about this restriction is what we call it. We'll worry about that later on. Right now we're looking at just this top portion, f of x or y is equal to x squared plus 1. Definitely getting ahead of ourselves as this is something we'll be covering later on this week. But parent function of the quadratic f of x equals x squared, we know what that looks like. I'm hopeful that parabola, U-shaped, opening concave up. But we have our transformation of adding 1. Now we know that we're going to be shifting that up 1. So what I'm trying to get at, I suppose, is that we're shifting it up 1. We know that the parabola is going to go right 1, up 1, left 1, up 1. Right 2, up 4, because 2 squared is 4. Left 2, up 4, because negative 2 squared is also 4. And this is what our parabola would look like. Similarly, now looking down at the second line, again, we'll forget about that restriction for the time being. Now this is saying, what if you had f of x is equal to x minus 1? Now, this is in our wheelhouse for sure. This is what we were talking about today in class in section 1.3 with all the linear functions. This is just a line, y equals x minus 1. We know that we have a slope of 1, a y-intercept of negative 1. So if this is our line, sorry, I need to, again, hopefully we're all okay with a rough estimate, rough sketch. This is what graphing the quadratic and the linear functions on the same graph. Obviously, this would fail being a singular function because, remember, for each input, there's a unique output. Let's just consider what happens at x equals 2, for instance. When x equals 2, well, are we here or are we here? When we plug in a 2 for x, are we going to obtain the value of, does f of x equal 1 or does f of x equal 5? Well, it kind of depends. Are we talking about being on the parabola in red, or are we talking about being on the line in blue? And that's where these restrictions come in. So we're saying that we don't actually have a full parabola. We don't have the whole thing. This parabola only exists when x is less than 0. So that means that for us, we don't have a full parabola. Again, this only exists when x, oops, did not want to do that. When x is less than 0, I need to get rid of some of that. Sorry, bear with me here. There we go. And everything that was less than this point on that parabola is still very much in effect. Now, you may also notice that I left this dot open. because this is showing that x is just merely less than 0. It's not including 0. If it were including 0, then I would most definitely have a closed dot. But these other points that I had drawn out there, they're not part of the solution. They're not there. Similarly, the restriction on the linear portion, this is saying that x is now greater than or equal to 0. So it's not this entire line that domain-wise is going from negative infinity to positive infinity. Instead, we're saying that this line only exists from starting at 0, going in the positive direction. So as x is increasing, that's there. But all this stuff that was happening or showcasing when x was less than 0 did not exist. So this is absolutely a function, singular, 1. This is a function because it doesn't fail the vertical line. The only spot that we may have some issue or some thinking that needs to go into it is at 0. Because, well, is 0 part of the top, the quadratic, or is it part of the bottom, the linear? So as you can see, where is it defined? For the quadratic, x is less than 0, but for the line, the linear function, x is greater than or equal to 0. So clearly 0 is going to be defined as part of the line, hence the closed dot, not part of the quadratic, hence the open dot. All right, so that's what we're talking about with these piecewise functions, is that we're evaluating various parts. So here in this particular case, let me get rid of some of these. In this particular case, first thing that we're supposed to do is evaluate the function when x equals -1. So what that really means, let me drag this over, what that really means is that we are supposed to figure out what is f of -1. So first obstacle that we have is determining, am I working in the top, quadratic, the red one, or am I working at the bottom, the blue one, the line? And we just have to ask ourselves, if x is equal to -1, is it the top that's true or is it the bottom that's true? So if I were to test this out in the top and plug a -1 in place for x, -1 less than 0, well, that's true. But down here, if I tried and I put a -1 and said that's greater than or equal to 0, that's false. That's not true. So clearly we're going to be working in the top. We're working up in the numerator. So we're going to work with the x squared plus 1. And now, as we were working on in the previous example, f of -1 means that everywhere that I see an x, I'm going to put a -1. So as I'm evaluating and cleaning this up, -1 squared is 1, 1 plus 1 is 2. So now we know that f of -1 equals 2, which means that I should have a coordinate when x equals -1, y, or f of x equals 2, and that essentially proves why I have that coordinate at -1, 2. All right, second. Now we're looking at when x equals 0. Again, not to be confused, this was when x was equal to -1. So now we're looking at when x is equal to 0. So what we need to get after here and now is to evaluate f of 0. Now, again, we have to pay very close attention to our sign. Our up top, in that portion of the function, we have x is less than 0 in the bottom, the second, x is greater than or equal to 0. So we know that we're going to be working with that bottom equation, that linear equation that x is equal to 1. So f of 0, again, just determining where is it that we're supposed to be plugging in. We have x minus 1, and everywhere that we saw an x, we're going to put a 0. So as we clean this up, 0 minus 1, which is -1. So we've established now that f of 0 is equal to -1, which means that when we put a 0 in place for x, we get a -1 back out for y, which again proves or showcases why we have this point right there at 0, -1. And then lastly, looking at, looking at when x equals 1. Again, the fancy way to write this out, f of, we'll go gold here, f of 1. Again, establishing which of my two options. Do I go with the top? Do I go with the bottom? Well, I know that 1 is actually greater than or equal to 0, so we know now, without any uncertainty, that we're using that bottom equation. And now when we go to evaluate, 1 minus 0, but f of, I'm sorry, f, I said minus 0, minus 1. X minus 1 is going to quickly become 1 minus 1. I'm trying to not give you the answer here, but I very much just gave you the answer. 1 minus 1, of course, being 0. That's how we know now that f of 1 is equal to 0, which tells us that when we put a 1 in place for x, we get a 0 back out for y, which once again is just going to help us to establish how and why that last point is where it is. So I went ahead and drew the graph because I thought that that may help, but you absolutely do not need this graph. As long as we can determine where does x fall, if we're evaluating x of negative, or when x is negative 1, 0, or positive 1, it's really just a matter of knowing and understanding, okay, which piece am I getting after, which piece am I going with, and we can go from there. So we had a homework assignment tonight, the yellow worksheet, 1.3 to 1.4. Give that your best shot, and if you have any questions, please come find me. Have a great night.